Hi, my name is Ramiro Flores. I'm an undergraduate student at UC Berkeley, majoring in civil engineering and emphasizing in structural. Today I'm going to talk about an introduction to phase diagrams. So I'm going to give an example and what constitutes a phase diagram. So first thing you want to know is, okay, what is a phase, right? So a phase is just describes, it's a description of a state of a system. So that's basically just says, okay, well, the phase here, in this phase, we have um, maybe liquid or solid, or maybe liquid and solid. Uh, so so hence why phase diagrams are actually useful. So here, let me give you an example of a phase diagram, because phase diagrams basically describe states. So because of the definition of a phase. So here's an example of a phase diagram. Here's one that you've probably seen in elementary school. You have, say, like pressure versus temperature, or actually let's just say the other way around. You have these curves going like that, maybe dipping down instead, like that, and then like that, and like that, right? And so this might be solid, this is liquid, and this is gaseous, meaning it's just as you increase temperature, you might have you get a melting point, and then here you might consider this a state of triple point. So that's triple point. So this is just an example of a phase diagram. All right. So here's another example of a phase diagram. You might have, which is a three-dimensional one. You might have pressure, temperature, and volume. So, and then another example is you might have actually a, okay, so anyway, I'll get to that a little bit later. So you might have something that looks like that, and might dip down, and might meet at certain places. Uh, and it's going to look kind of carved, the phase diagrams that are 3D. So these are just basics, like physics ones that you may have seen, or not in high school, maybe not, most likely in college, community college. So yeah, you have pressure, and it's worth noting that let's say if you take a cross section of and where V will be one axis, T will be one axis. Actually, let's not. Actually, I'm sorry. I meant to say that. Let's say we take a cross section and P will be one axis, V will be one axis. So you might take a cross section where P is here, this is T, and instead now you have these curves going like this, maybe. So you'll have these curves, and so this is called an isotherm because, oh, I'm sorry, volume. So this is called an isotherm because we're assuming that they're all at the same temperature, each contour line. So so that would be an example of another phase diagram. So these are all phase diagrams, and so later on you're going to be seeing very complicated ones, because not only do phase diagrams also can be described can have variable volume, pressure, and temperature, but it can also have variable compositions. So, for example, let's say in the x-axis I have composition of carbon, right? So carbon, and we're saying this is weight percent. So let's say like the maximum amount is 6.67%, and then the minimum amount is obviously 0. And so then you have this weird looking curve like this, maybe. So and so then you also have another curve going this way, maybe. Actually, sorry, the other way around. And so let's see. That would be this way. And so let's say this is solid. I'm sorry. This is some kind of phase, right? So this would be solid, and maybe this is liquid. And so basically, and then here we have temperature though. So we have temperature versus composition. This is a lot different than any of the phase diagrams that you might have seen in physics or chemistry, because now what we're doing is we're taking the state variable is now going to be the composition. So so this is actually very useful because because what it does is it allows us to figure out basically compositions of states. So this is actually more particularly describing an alloy. And so this is going to be important in material science. All right, so I'm done with the examples. So what constitutes a phase diagram? Well, the first thing that constitutes a phase diagram, so phase diagram elements, or let's just say, yeah, elements. So the first one is going to be that that the solution, or whatever you're modeling is at equilibrium. You must assume that because basically you'll never have in a phase diagram time. So that's the reason why the solution is going to be at equilibrium. Also, usually, and I'm trying to figure this out because it's not very obvious, but usually you're only modeling, and I just say modeling just as a general term. So basically, modeling, or just taking a description of homogeneous mixtures or pure substances. So what that means is that whatever you're using is going to have definite proportion usually, and almost like and what I mean by that is about 99% of the time. So like 99% of the time you're going to be using the phase diagrams for homogeneous solutions. So we assume that alloys are homogeneous because they have a definite proportion, even though they're actually physically combined. So that's what usually constitutes a phase diagram. All right, thank you. Thanks for watching. Hopefully you can understand that and you enjoyed.